So let me explain what's happening in this figure here. What this figure is basically doing is giving you a picture of the activation and inactivation properties of the sodium channels. Now you remember that sodium channels alternate between open and closed and inactivated. And these are all voltage dependent transitions. So what we want to know is, how does the opening and the inactivation depend on voltage? How can we figure that out? So usually what we do is to do first of all, let's think about inactivation, first of all. Measuring activation is fairly straightforward, because what you do is you run a series of depolarizing steps, which is what they're doing down here, and then you measure the currents in response. And then you then take the amplitude of this current and plot it against the voltage, and what you get is a relationship a bit like that. So that's current and that's voltage. To work out the activation, you take this line here, because at this point all the channels are open. You extrapolate down, then you measure at each point the ratio of the current size to what it should be if they're all open. And that gives you this. So each point along this curve here represents the proportion of sodium open, or better still, conductance G over G max. So it's G over G max. So what we're interested here is this value along here, which is the 0.5. It's V, what we call V half. It's the position, or it's the voltage at which half of the conductance is available. In other words, half the channels are open, if you like. And what they're showing you here then, this curve shows you the dependence of the closed to open to inactivated back to close. This here is describing this transition between closed and open. Alright, so what about inactivation? So remember that what happens when the sodium channels are out, they open, and then they go into this inactivated state. So here they open, now they're inactivating, and then when we turn the voltage off again, they're closed again. So how do we measure this here? Well, it's actually quite clever. What you do is you do two steps. I'll start with a second step first. Right, so start at a low voltage, minus 90. Then you do a step to some sort of positive voltage, and then back down again. So only one step here. And so this is going to be about +10, where you know all the sodium channels are going to be open. Now that should evoke a current for somewhere in this region here. Right? So this voltage here needs to be in this region so that you know you've got G over G max is nearly 1, or the channels are going to be open. But here's the trick. To get them to inactivate, you precede it by a long pulse that itself will evoke an inward current. And then what you do, you now have when you go to this step here, you're going to get a much smaller response because some of these are still in the inactivated state. So what you've done is you step to this new voltage here, and during this time here, you're allowing all the inactivation to take place, and then you step to a test voltage here to see how many channels have remained inactivated. So you don't just do that once, you do that to several levels here, and then you find that if you start with a very low level, if I erase all this, so first of all we have a low inactivation pulse and then a big activating pulse, and we should see here maybe a little bit of a response and a full-blown response to that one. Then we go higher voltage here, we might start to see something happening down here, and this one starts to get smaller. We work our way up, and this gets smaller and smaller and smaller until it eventually disappears. So now what you do is you measure the size of the current here, so how big was the current, and then you measure the voltage here, and these two are this. So in other words, as your pre-pulse here, if it's a very small one, minus 120, we get full-blown responses here. But as that pre-pulse gets more and more positive, this one gets smaller and smaller. So we've now got activation, we did that before, and inactivation. And once again, we look for the V half, this time of inactivation, and this value here tells us the equilibrium position for this transition. So we've got activation and we've got inactivation. And there are also similar ways of doing this with here, but that's not looked at in this study. And the key point here is that for CN, in the presence of CN21, this shift here is significant. It's shifting inactivation to the right, to a more depolarized level. So in other words, the voltage at which half of the inactivation occurs is slightly more positive. So they're inactivating at a higher membrane voltage. So you're getting less inactivation. And similarly, activation, exactly the same thing. There's a rightward shift here, and so it's taking roughly 5 more millivolts to activate this channel. That's really small. So the question is, we've got statistical significance, because that's done down here. We've got all the data down here, so it might be significant, but is it biologically significant? Does 5 millivolts really make a difference?